India has a very big semiconductor mission. I have with me Dr. S. Somanath, former chairman of the Indian Space Research Organization, best known for his soft landing of Chandrayaan 3 nearer the South Pole. But he has also created history by giving India the first chip called New Generation Vikram chip. And the Prime Minister received and unveiled that chip. Thanks a lot for speaking to me.
Thank you
Dr.
so much.
Somnath.
Thank you so
It's
much,
been
Pallava.
It's been a while since we spoke to each other. What is this Vikram chip and why should we be proud of it?
I must put the credit of making this chip to some of the individuals in Vikram Sarabhai Space Center who worked in my team when I was a director there, especially Sri Mukaya, who retired as the associate director of Vikram Sarabhai Space Center, who developed much of the compiler required for this software work which was required for this, and also a very small team who actually did the design of Vikram 32 and then translated the design into the Vikram 32 chip using the 180 nanometer node at SCL. So
Which is the semiconductor complex in Chandigarh.
yeah. So first thing is to compliment them, not me really, for such a wonderful achievement. That the today it was unveiled as part of the Semicon India 2025 by Honorable Prime Minister. It was a proud moment for all of us to see that. But it was a vision that the ISRO took it on itself from the first generation Vikram, which is a 16-bit processor with a von Neumann architecture, to a next generation Vikram using the same technology of the SCL, which was the only thing available to us, which can do much more complex problem solving for rockets, because the rockets are now becoming more and more complex in terms of the software, sensors, sensor fusions, and computational load that is coming on.
Tell me a little bit about the qualities of Vikram. What are the specialities?
That is specifically which I am coming to. One is the Vikram 16 served the purpose for many years in building PSLV, launching. Many of the computers were done using.
Again made at SCL Chandigarh.
Again made at SCL. Initially the chip was, the wafers were made outside, packaged at SCL. Later the wafers were done within SCL. Then we developed the packaging and qualified it for use in mission. That also was something which during my tenure as director we accomplished using our really Indian Vikram 16. But Vikram 32 primarily came because we need to have higher clock speeds. And the higher clock speeds and more memory on board the processor itself allowed us to pack a lot of other data into it as the data which is required for the computation to happen, and also achieve a whole lot of computation much more shorter time cycles. You know, in rocket everything happens very, very fast. So we have something called a minor cycle of operations and a major cycle of operations. The minor cycle of operation was typically for our rockets 20 millisecond.
20 milliseconds.
Yeah. In 20 millisecond, one cycle of entire computation required on board has to be completed. Then it has to post the state or the next set of commands to the actuators or sensors. So the acquisition of the data, processing and posting all has to be over in 20 milliseconds. 20 milliseconds is not a short time, it is a sufficiently long time for computers. Okay. But the point is now we wanted a still shorter time for missions like reusable launch vehicle, human spaceflight mission, etc. And for operation where there are more sensor data coming, 20 millisecond was found to be inadequate. So generally we use out of the 20 millisecond, almost 17, 18 millisecond were consumed for typically GSLV for Vikram 16. So we were reaching the boundary of the computational time available. So we need to make it more relaxed with a lot of cushion in that. So that was one requirement. And second is, in the vehicles like reusable launch vehicles and future missions, there are going to be a lot of onboard decisions. And in addition to the sensors in the rocket, we are going to have additional sensors. You know, typical sensors in rockets are inertial sensors like the gyros, accelerometers. And this gives input and we have the navigation happening using that. And there are other inputs coming which finally decisions are taken. And this is also becoming more complex because software.
And these are all automated.
All automated. So basically we wanted more precision in computation. For example, you call floating point operations. You allow number of digits that you can handle in for every number. So there will be a truncation. If you use for previous version, there will be a truncation. This truncation will give some errors. So when you allow larger extent of precision, truncation errors will come down. You will become more accurate in terms of your computation, and errors will become lesser and lesser, and the overall time cushion available for this will become much better. So this was the reason for us to start this effort. So when this new computer chip has to be developed, then we started working on Vikram 32. Many features were added first is in terms of the clock speed increase, in terms of the onboard memory that you can do, in terms of the instruction set that you are actually putting in the processor. Then the compiler, we call it compiler, that is our own ADA based compiler, which is the software standard which is meant for aerospace, which gives you high reliability that while you are doing this, you get that type of quality of compilation. But we are now started developing a C compiler also, which is on the process. Sri Mukaya was doing that work for post retirement also. He was contributing to building that capability. Then we were also making interfaces for the communication protocol called 1553B protocols, which is required to communicate the computer with the rest of the peripherals and other nodes within the bus. So that protocol, very lower voltage for operation, which guarantees you for lesser heat generation and more thermal stability for it. Then the mounting of the chip was becoming better. That is called packaging of the chip was better to have more ruggedness and stability and etc. etc. Then we also made a graphical user front end where the real operating, that onboard software which you are developing can actually be compiled and you can see the really on it. So it's again our own development. So all put together, when Vikram 32 came, now of course, when a new chip is coming from foundry, then we need to be very cautious before putting it in rocket. So it goes through actually a processor development, a computer development. A computer means not only the processor, along with all its peripherals, interfaces, everything. A card was made and we tested it quite a bit using lot of test beds. So you need to write a software also correspond to the new computer. That work was going on for 1 or 2 years. Then we want to test it in PSLV. So before we actually put it in typical in PSLV, normal technologies that we will put a piggyback. No, do the same process which is happening in a traditional computer in this also, and compare and see how both of them are performing in a given mission. And due to the environment of space, is anything harmful happening. And we did in one of the mission called POEM, and the result was extremely good.
So was it on the PSLV or was it part of the POEM? Because the PSLV also has redundancies you incorporate many times.
Yeah, but redundancy is only in terms of the computers. But then this is a separate set of computers. POEM was a separate set of computers. And what it does is, after the PSLV satellite injection is completed, the control of the whole upper stage of the PSLV get transferred from the traditional computer which was existing Vikram 16 to this new computer called Vikram 32.
Okay.
So there is a transition happening, and the Vikram 32 computer to control start taking control of the upper stage now. So entire attitude stabilization, that means its orientation, all the payload operations, the data transfers, communication, and all management was happening using the POEM computer which was based on Vikram 32.
So did it succeed?
It succeeded. It's not only succeeded that it actually did a launch vehicle mission. Launch vehicle mission lasts only 15 minutes, 20 minutes. So the chip function is over. But this Vikram 32 survived for 30 days. Post that separation, the POEM was working in orbit for 30 days. And for the entire 30 days, this chip worked. And the entire POEM payload operations were successfully accomplished. And we have other features there. So you could switch off the computer, we could switch on the computer, we could reboot it and again reinitialize it. So there are many features we added in this POEM which allowed us a lot of new flexibility like what we did in Chandrayaan 3.
So essentially stepping towards having an Indian semiconductor ecosystem?
No, that point is very, very important. I think doing some of this really reflect that with whatever semiconductor industry ecosystem that we were having, traditionally, the SCL was the only thing, and some other small labs which are available for other type of technologies. We were able to build quite a lot of devices for us as indigenous devices. But I believe Vikram 32 is the highest of what we did till now. As far as the technology and knowledge of the people in ISRO and SCL are concerned, I think we can claim to be really, really wonderful work with the the power of the foundry and the power of knowledge of the semicon designs were fully utilized to develop that process.
So we'll use it in Gaganyaan?
I believe in Gaganyaan we can definitely use it. That decision is to be taken by the appropriate decision makers in the organization. But I also want to tell you that along with Vikram 32, we developed another chip also.
Another chip?
Yeah. At the same time, this was going on in VSSC. It is called Kalpana 32, which is based on a different architecture. It's a RISC-based architecture. I told you the Vikram 32 is a von Neumann architecture. So this is a pipelined architecture which gives you a little more capability in terms of the computation. But it's not, I cannot say it is a fully Atmanirbhar or fully done in India. The wafer came from outside. But the design is ours and the packaging was done in SCL. So this processor also is developed. We made a computer out of it. We tested it. But the software architecture will differ because the compilers are different. Some of the compilers and some of the elements are bought out because it is a RISC architecture, which is an open architecture which you can adopt for using in processor development. Whereas the Vikram 32, I can tell you that every single thing in the Vikram is our own. So there is no knowledge or element which is brought out in this, including the technology.
So is it silicon or is it compound?
It is silicon only. Compounded semiconductor is still not being used for this yet. But there are a lot of other devices being made using other compounded semiconductors in other laboratories.
So do you rate that as a higher achievement than Chandrayaan 3 soft landing?
No, each one is a different achievement. No, we make progress in different domains, you can highlight that. As far as a mission to an interplanetary body is concerned, of course, Chandrayaan 3 was the epitome of that. But with respect to a silicon-based device they're making, of course, Vikram 32 is an epitome of what we have achieved till now. But I think greater journey is waiting for us.
Thanks. Thanks a lot for speaking to me, Dr. Somnath. There is so much to learn from you at every stage, whether as Chairman ISRO, whether as Project Director of GSLV, or as somebody who's given us the first big success in a chip. Your contributions have been superb. Thanks a lot. So that was Dr. S. Somnath, former Chairman of ISRO. Maybe we will remember him more for giving us a chip called Vikram. Chandrayaan 3 soft landing was an incredible achievement. But this chip is going to power India to a Viksit Bharat, maybe a smaller one. In Bangalore, Pallava Bagla for NDTV.